Perfect. Thanks, Toby, and good morning from my side as well. So for the next 20 minutes, what I'll do is I'll explain a bit about what we have been doing at MaintPartner around using machine learning for industrial automation data and trying to answer the question, does it really work? And if you have any questions after the presentation, we're right across the room in our booth to answer. So first of all, we started about 4 years ago looking at this problem at MaintPartner in terms of we have a lot of data available with our customers. How could we use that more effectively to make good decisions? And specifically for our customers, how could we reduce the unplanned downtime? So that was the initial scope of what we started to look at. Now, we have 3 simple questions before we committed significantly into this endeavor. First of all, is it a real problem? Is it really happening to most of our customers? Do we think we can solve it as MaintPartner? And finally, is it really worth solving at all? So if we look at unplanned downtime, it's something that happens practically with all of our customers. So it's happening all across the board. And most of it is caused by unforeseen equipment failure. So that was already discussed in the previous Caverion presentation, for example, that equipment failure is by far the most significant reason for that, even though all the systematic problems have been removed, or most of them have been removed. So if you have equipment that continuously fails, you are likely to fix it, and this is something that we cannot really help with. So we have equipment failure causing a lot of unplanned downtime. Systematic errors have been removed, so all that is left is really these kind of random events that happen across the process, across your factory plant, across your power station. So it's very difficult to start thinking at how do I use machine learning if it all looks pretty random. It's very difficult to model. And finally, there were no warnings from existing automation systems in many cases for the downtime. Or either there were too many warnings and nobody was looking at that, or the warnings came way too late for actually somebody to react to them. So we thought, okay, it seems like a real problem, right? The next thing we thought about, okay, can we really solve it? As MaintPartner, do we think it's solvable? I mentioned earlier, there's a lot of data available. So huge amounts of automation data that is accurate, high quality. We thought, okay, that should be a go. The recent developments in cloud and IoT, which I've been personally looking at for the past 9 years, make it really easy to get the data stored centrally into the cloud using some of the famous cloud platforms and standard APIs and so forth. So, okay, that's also supports the theory. We have the data, we can easily transfer and make it available. Now, about 4 years ago, we started to also see a lot of development in the machine learning AI space, and we thought, okay, if you put all these together, we have good data, we can make it available, and we can use AI machine learning to use on that. And finally, we think we have the domain expertise as a company to do it. We said, okay, fair enough. It's a real problem. We think we could solve it. The last question about money, is it worth solving at all? Most of the customers we work today report something between 5 and 15% of annual unplanned downtime. So if you're running 300 days a year, that's between 15 and 45 days per year of unplanned downtime. Daily cost with the customers that we work with ranges between 25,000 to 250,000 per day, which is low compared to many manufacturing areas. So even if you calculate those together, the annual cost of unplanned downtime is millions of euros. So it seems like a problem to really deal with. Okay, so we said, let's do this, let's start investing and seeing where this leads. Now we had to make a number of choices and focus what we're doing in this domain. And these are the 4 main choices that we've done. The first was about size of data. So there's a lot of data available. Do we use all of it? Do we only select certain subsets? Or do we even go for picking out certain KPIs that represent the entire production plant? But we discarded these as we wanted to look at the entire downtime as an issue and think about how we could also not notify only the KPIs and their changes, but also all the potential early indicators that there will be a problem. So we thought, okay, let's use all of the data that is available as a starting point. The second decision was about type of data. So do we use just that automation data? Do we need to install additional sensors? That's also something that has been discussed a lot during yesterday and today, how easy it is today to install additional sensors, vibration sensors, temperature sensors. We thought, let's not go there yet. Let's start with the existing data and see what we could do with that. We also decided not to go into using human-entered data, let's say things like maintenance logs or other comments from the maintenance personnel, just because it's very different. Quality is very bad. Sometimes it's very good, but in most cases it's very bad. So we thought, okay, let's not use it. So we're only going to use all of the data existing in the automation system. Then we had two more choices. How about the timing aspect? Do we only look at the current value of those variables? Or do we also think about things like accumulation, let's say accumulated machine hours, or accumulated flow of a liquid? Or do we even consider things like delayed correlations? So there's an event happening somewhere else, and then after half an hour, there's a correlation somewhere else, which we think is really valuable, but also relatively complex. So we thought we're not going to go there. We only focus on the current information that we are reading and what it looks like. And the last decision that we did was around automation. Do we want to make it highly automated? So it's kind of, it figures out what's happening and then automatically guides the operations, for example. And we ended up saying, no, we're not going to go there. Let's keep the human in the center. Let's provide good insights that people can act on and also validate and feed back into the system. And of course, these are, depending on what you're trying to do with machine learning, these are the kind of choices that you would also have to make. And once you made those choices, then that will limit, in a way, what you can do and what you can expect as an outcome. And these are the choices that we did. Now, after these choices, we said, okay, this is our approach. This is how we're going to go about it. So we have existing data, huge volumes of that data. We're going to use all of it, look at the current time, look at the correlation on the data, and then use the machine learning algorithms. And then we faced quite a bit of challenges in the first projects. And I'll show you a couple of examples of cases that we've done. We've found some good insights, but we had a lot of failures. I'm not going to go into details today, but these challenges and the learnings have come from those failures earlier. So first, the data. We decided to use all of it. Now, in some of our customers, that means a lot of data. So we had one single customer for example, in the steel industry, we're collecting 50 millisecond data, simple data, just key value pairs. In a couple of months' time, we had 2 terabytes of data. So just moving that data, storing it, and analyzing it in more or less real time is really challenging. That was number one. The other is the quality of the data. So we know, we're looking at the data, we know it's accurate, but there's also periods in that data where there are problems, let's say in the site or in the process. How do we make sure that that data, the bad data, does not enter the retraining process of the machine learning models? And there we ended up by looking at the solution that can we help the human to be more active in that role of selecting when we get a warning, selecting what parts of the data will go back into the retraining and which ones are not. This is still something we are working on. It's not something we have solved fully. The connectivity side, I mentioned the IoT and cloud solutions are becoming better and better all the time, but there will still be delays of the data. There will be breaks, 2 hours break, 24 hours break. The key thing is to be able to handle these breaks and decide what you need to do. So we have opted to do this on a customer-by-customer basis and have a discussion. Okay, so if we have let's say, a 6-hour break in the data, which one is more important? Do we need to be up in live monitoring immediately, or do we fill back this gap? And then with the assumption that for the next X hours, we will be with a lower response time in the analytics. So that's connectivity. The model performance is kind of the crux of it. So how well the models actually behave with the data. And in the model performance, there are multiple things that you can also select or aim at. And one of these things for us is we are doing anomaly detection on a power plant, as an example. So any deviations that come, we will raise those as a warning. If we would target a very high true hit rate ratio, that we only notify you if there's a real event, that would mean that we will miss a lot of events as well. So the idea that we had is, okay, we're not going to aim at 80 or 90% hit rate, but it should be more than just a couple of percent, which would mean that you would have 100 warnings, only a couple of them are real, and in the end, people just turn off the monitor and not look at that. So we are typically targeting about 20 to 50% true positive hit ratio over time as we go forward. And that will give good enough warnings, but also lower the risk of missing real events in the factory. The biggest challenge, though, is the last one, change management. Now, in most cases, we are introducing new technology with machine learning in a relatively low-tech environment with people who have no expertise and experience. You go and talk to a person that's been in a power plant for 30 years, for example, and you go to tell them now, next time you get a warning from this screen, you should go and look at that. And they will say, no way, I just open the door and listen, and it's okay. So this kind of change of getting people to actually believe and act on the findings that you will have is been probably the biggest learning that we've had. And what we've done is we've taken an approach that, I think it was mentioned yesterday also in the speak, that you can't just throw over the data, that somebody do tricks with it and then you get answers back. It has to be a very collaborative process. So what we do in the projects that we run today is that we have initially daily meetings, then weekly meetings, and in the end monthly meetings to make sure that the people who are actually using this stuff really understand what we're doing, how their role or how they are needed in the entire process, and so forth. So these are things that we've really kind of struggled with and kind of hit our head against the wall many times, but now we think we have a pretty good concept of understanding where what we have built, where it fits and where it doesn't. Now, a couple of example cases of things that we have been able to catch, and these are very simple examples. I selected them intentionally to be very simple. Here's a manufacturing case. What's common to these cases is that there was no warnings of any other systems. You have automation systems in place, you're monitoring all this stuff already, but there's no warnings, no information. In this case, what we saw, if you look at the graph, what we saw is that the air humidity started rising, and it was more than what we expected at those operating conditions. So the machine learning algorithms have done their magic. They understood that, okay, with all the other parameters being what they are, this humidity is too high. And we notified the customer, and they went and examined the situation, and they found that there was a steam leakage in a radiator that they were using to dry the air. Now, in this case, they were able to fix that immediately during a normal planned downtime break, and there was no real impact. If they wouldn't have seen that at that point, in the next run or one of the next runs, they would have most likely had serious downtime and also waste of product. So very simple case, and what we do is then we continue to monitoring this in a way we've done earlier. The other example is even more simpler. This is from a power plant. So you have a generator that is hydrogen cooled, and what happens is that hydrogen will leak into the turbine hall. You have two exhaust fans that will remove that hydrogen because it's flammable explosive gas, so it poses a security risk. And you have two fans for security, so always running. Now what happened in this case was that the other fan just stopped working. And again, no warning from the automation systems. They were not monitoring that individual signal. They had the signal, but there was no warning that if it breaks, you should do something. We didn't know, but what we saw is with the anomaly detection, we picked that this has always been working, always been running. No, it's not. There's an anomaly. Please go and check it out. And it's a very low-cost fan. It doesn't cost a lot to fix it. But the situation that we were able to avoid is that if now you're left with only one fan, if that would fail, and you don't know about that situation, if that fails, you have not only a potential big downtime, but you have also a serious security risk if you start to get hydrogen into the turbine hall. So very simple, but of course, as an end result of this, now they are monitoring this in the automation system as well. So this is not going to happen again. But these are very simple examples of the things you can find out from the existing data that you would kind of expect that are already handled with existing solutions, but are not. So if we look at these examples, And most of the cases share similar type of descriptions. There's been no alarm systems that have been reporting it. Typically very simple cases, and if you look at that afterwards, you say, well, I would have seen that. If I would have been looking at this specific measurement, I would have seen that. Yes, that's true. But you have thousands and thousands of measurements. If we look at a typical power plant, we look at typical process environment, you have thousands of measurements. And you don't know necessarily which ones will be the early indicators. And that's why machine learning is really, really powerful. Now, what are we doing next? There's a couple of things that we're really, really thinking about at the moment. Number one is to make the decision support even better. At the moment, we will show a warning that something is amiss. Something is happening for the first time, and the customer will go and check it out, and they will make their decisions. Now, it would be very nice to provide more information. Has this happened before? Has there been a similar event? If so, what was done for that similar event? What is the maintenance history of that specific asset that this signal belongs to? And these are kind of things that we are now looking into. So providing better decision support for the person that will eventually make the decision. And actually the role of the person in the whole process is not only that decision making, they are also involved in the early stages of the project to make decisions of if there is data that we should exclude. Once the machine learning algorithms do the initial training, they will also be validated by the human user. See, does that make sense? Does this grouping that we have created of the signals, does that really make sense? Is there any real-life correlation between the signals? And finally, then, when we have findings, they will go to that human for interpretation. The other thing we're looking at is pretty obvious. We already have the data available. Could we use that not only for anomaly detection, could we also use that to improve the process, kind of create a benchmark surface and try to find out how we can get closer to that optimum way of, for example, running a plant or running a factory. That's something that we're doing at the moment already in the kind of early project stage. And the last question is about more automation. Should we try to make these things really autonomous? That if something happens, you automatically change something in the operation process? Maybe, but this is something that we are still thinking, and it could be in very limited cases possible, but only with certain high critical assets and very potentially, let's say, high security risk environments. Otherwise, we would keep the human always in the loop and in the center. So maybe closing in on the original question. So does machine learning, can it work with industrial automation data? I think we can easily say that yes, we can make it work, but it's not a generic kind of magic trick that you just give all your data and then you will find out a lot of things about it. You have to really pick a problem and then make the choices that I mentioned earlier. What data you will be using in terms of amount of data. Are you using only the automation data? Are you also including textual data and so forth? Once you make those decisions and you stick with them, I think there's a good way you can make this work. For that, I'll thank you for your interest. And if you have any questions, please meet us in the hall. Thank you.